Hello students, welcome back. The final topic here is the interval estimation for population variances. And of course, taking square root, you're going to get interval estimations for population standard deviations too. For that, you have to understand something called the chi-square distribution. Remember, we are talking about variances, so they are obtained by squares, all positive. And chi-square, again, is also positive, obtained by squares, and so on. Here are some graphs of chi-square distribution for some selected degrees of freedom, 1 to 5. And as you can see, as the degree of freedom increases, the curve recedes to the right. So this one is degree of freedom 1, 2, 3, 4, 5, like these. It is known that the inference on population standard deviation can be done like this. Degree of freedom is, as usual, n-1, and chi-square quantity turns out to be degree of freedom, nu, times s squared over sigma squared. And nu is n-1, so replace n-1 here, then you're going to get the first formula. Actually, and replace n-1 here, and then solve for sigma squared, then you get the first formula, and solve for s squared, then you get the second formula. So it depends upon what you want to do. They don't really look exactly the same. Okay, they look a little bit more symmetrical, all right. All right, sigma squared is like this, s squared is like that. Okay, and you're looking for sigma squared, right? S squared is already known, it came from sample, so you know the value. So degree of freedom, you know that. And sigma squared is the quantity you're looking for. And look at sigma squared versus chi-squared. The inverse. Chi-squared is in denominator. So the inverse variation you're looking at, basically. Sigma squared versus chi-squared. So if you have a graph of chi-square distribution, remember the inverse. And then graph of chi-square distribution is asymmetric. To the right, it can go forever toward positive infinity, at least theoretically. To the left, stops at 0. We have asymmetric. So we have to consider left-hand side and right-hand side separately. And then left-hand side and right-hand side, from the first relation here, they're reversed. So right-hand side endpoint will give me the lower bound of sigma, and left-hand side endpoint will give me the upper bound of sigma. Does it make sense? Well, it will begin to make more sense if you actually sit down and do an example problem. So let's go ahead and do one. Please stop the playback and read through the problem. Okay, this is about concrete pressure. And here's the data. And then let's see, what's the mean? 37 point something. What is the sample standard deviation of this? 2.571 something. So this quantity is the best point estimate. And then around that, you're going to have that asymmetric curve. All right, find the 95% upper confidence bound of the standard deviation. Here's a picture. We have this asymmetric picture. And then let's see. asymmetric picture here. This is for chi-square distribution. And then remember this inverse relation. So we have to find out the left-hand side lower bound for chi-square. So how does it work? Well, here's a formula, and that formula, as a matter of fact, I don't remember. Always I have to look this up. Sorry about that. So this is what we want. And for n minus 1, let's see. How many experiments did he do here? How many numbers are there? Okay, there are 15 experiments here, 15 measurements. So the degree of freedom is 15 minus 1, so degree of freedom is 14. So here, this is going to be 14. And then what is sample variance? This is sample standard deviation, 2.57 something, this one. This one squared is the sample variance. So put in that one squared. Now, let me just increase this font only. And then you have to get appropriate chi-square value from your table. Okay? And remember, reversed. So we are looking for upper confidence bound, so we have to get left-hand side. Okay, where is your chi-square table? Let's go to chi-square table. Here is a chi-square table. Shading is to the right. But here I want shading to the left. So 5% shading here, which means 95% shading to the right. All right? Let's go to that table. 95%, where is it? Here, 95%, 0.950. And then where is the degree of freedom? Sample size is 15, so degree of freedom is 14. So go down, down. 6.571. This thing is, excuse me. .571, degree of freedom of 14, and then for 95%. 6.571 replaces the chi-square value. You don't square this again. This is already square value. 6.571. All right. This one is 6.571. Oh, come on. 6.571. This is approximate equal. All right. Let's run the calculation. If you do that, you're going to get 14 point something. And therefore, the sigma value that you're looking for is going to be approximately the square root of this. 3.75 something. And this is upper bound. Remember, reversed. So we wanted upper bound, so we get the other way around, left-hand side. shading. Well, this figure is a little bit more accurate because I use Mathematica's computation. This one I got from the chi-square table. Well, pretty much the same. Okay, next problem. Find the 95% lower confidence bound. Again, remember this. Sigma squared, chi-squared, inversely related. So if you want lower bound, I have to go the other way around. So the picture is like this. 5% to the right. So this one, I don't remember. I always have to look up. And in this case, degree of freedom is 14. And then S is standard deviation of this data. And then divided by chi-square value for the right-hand side shading of 5%. 95% here to the left, 5% to the right. Now let's look up the chi-square table to find out this chi-square value for this right-hand side shading. Ready? Let's go to the table. So previously we were 95% here, but we want just 5% here. So 5% is here. And then sample size is 15, so degree of freedom is 14. So we are looking at 5%, degree of freedom 14. We are looking at 23.685. So that is my chi-square value, 23.685. 23.685. 23.685. Again, you don't square it again. It's already chi-square table. So chi-square value is 23.685. Let's calculate this whole thing. Let's ask Mathematica to calculate. I'm getting 3.90 something. And this computation, by the way, is done by Mathematica, so a little bit more accurate. But as you can see, they are very, very similar to each other. And of course, this is variance. So you have to take the square root of this. So your sigma value is going to be square root of this. Oh, by the way, this sigma is for lower confidence bound. That's going to be square root of this quantity. .977, and that is the lower bound. 95% lower bound. Here's a solution. Yes and yes. So we found out 95% lower confidence bound. And then previously, we found out 95% upper confidence bound. Put those two together, then what do you get? Do you get 95% confidence interval? No, you get 90% confidence interval, because you see 90% in the middle, so 5% here, 5% there. So if you want 95% confidence interval to begin with, then you should have looked for 2.5% here, 2.5% there. So you should have done 97.5% upper confidence bound and 97.5 lower confidence bound. So for example, if you wanted to find 95% confidence bound and confidence interval to begin with, then you need 97.5% lower confidence bound and 97.5 upper confidence bound. Picture will change accordingly. So in the middle, 95% now, 2.5% here, 2.5% there. Did you notice a change of the picture? Previously, it was like this, so only 90% in the middle. So this was smaller, larger here, larger also there. Now 95% in the middle, 2.5% here, 2.5% there. Picture will change accordingly for 97.5% lower confidence bound. Remember, reverse, the lower confidence bound is to the right. And then let's change this one to 97.5%. Upper confidence bound. So blue got a little bit larger, and this one shrunk from 5% to 2.5%. We want upper confidence bound, so this is to the left. So this formula here, how should I rank this formula as level of importance? Oh, good question. It is definitely within top 10, but I don't know. I don't memorize this formula. I always prepare something and look up. Never memorize this formula, so I don't really regard it really highly. But of course, whenever you have to do this interval estimation for population variance and standard deviations, you will have to use this. You see, degree of freedom is easy. S value is coming from the sample. Chi-square is the quantity you have to look up. And remember, sigma squared, chi-squared downstairs. So they're reversed. So we want upper confidence bound, then shading is to the left. You want lower confidence bound, then shading is to the right. It's the other way around. If you remember that, and you'll be okay. Alright, so much for section 4, and that concludes lesson 10.